Good morning. This is now November 13th, 1 week after the big snowstorm started. So I'm back in the classroom, and the big excitement for today is, will the projector go out? Because I filed one more issue 2 weeks ago after it went out, and then I didn't get to test it in the classroom last week, so they did something more, and we'll see if that something more makes a difference. So there's lots of things happening right now because the momentum is building rapidly for the end of the semester. Most of you are probably thinking about your Thanksgiving holiday already, Christmas, other family things going on all in between. And there's a lot of things up and running. I've pushed more content onto the website last night, revised some things again this morning because I can never seem to get it right. There's so many details out there. I still have a homework assignment to grade. Hopefully I'll get working on that this afternoon. And we'll just see what else I'll come up with to talk about as I overview where we're headed. But let me just start by opening up the calendar, which I frequently do, especially towards the end of the semester. You can see where we are here on the 13th. Next Wednesday, I intend to wrap up Chapter 5, which we'll be spending quite a bit of time on today. And on Thursday or Friday of next week is when you're going to get Exam 2 as a take-home. That will be pushed onto the website. I've made some preparations, and we'll talk about that in a minute or two here. The week after that is the week of Thanksgiving, so as you look at that, you see the 27th as the day before, and that's the date that I'm planning on being the latest date for turning in the take-home exam. In the past, I've made it Tuesday evening, but I'm going to make it by noon on Wednesday, the 27th. Project number 1 is also up there and running. I've eliminated problem 3, and we'll talk more about going over problems today, especially the Pi audio problems. I've generally wanted to have that due on the 27th also. We'll just see next week whether or not I have to extend that into, say, December 2nd or something like that. It absolutely has to get off you have to get done with it because there's other things to get done. There's a problem assignment due on Friday, which is based on probability, random variables, and random processes. In particular, it covers probability review, and it also has quantization noise. It's 3 problems plus a 4th bonus problem on anti-aliasing filters, which we'll be talking about and wrapping up on today. So the class is not full. One person is here, so I can't get immediate feedback from all of you, but that's where we're at. And of course, if I slide down on the calendar, you know that we have 2 weeks in December of regular class, and then we'll arrive at the 18th, and that is the day of the final. And that will be an in-class final. I put a review sheet up from 2018 because that's what I could scrounge around and find, but that's just a placeholder, so I have an idea of where we're headed on that too. I definitely encourage you to hang out and look on the website. I pushed this out last night. I actually had more stuff that I pushed out since I wrote this section for 11-12. So there's just a lot of things showing up. So I'm going to spend a moment here just looking at what I've added. First off, I did update the project. I had it in the wrong section of this page in the tab section. So it is officially now fall 2024, and I've deleted problem 3, or say omit. I've updated the Jupyter Notebook for problems 1, 2, and 4. So that really what the zip package does there, it deletes things that were associated with problem 3, the old problem 3, and then the separate notebook for problem number 5, which is all based on using Pi Audio Helper for real-time DSP. That's been updated as well. The biggest thing I changed there was I now have embedded inside of that sample notebook a Windows 11 listing of available devices for audio. It used to be from my MacBook, which for most of you that's not what you're going to be using, and we're going to go through that again today. One of the things that I didn't put in the list originally for putting in your Conda install, and I got hit by this last night on this machine, is had not installed iPy widgets. So if you haven't put the widgets on, it's just from your Conda prompt in the virtual environment for Python 3.9 that I asked you to create, just say Conda install iPy widgets. You'll get feedback on it if you haven't done it, because it will say what are the widgets. It won't know what they are, and once you put them on there, you'll be good to go. So problem sets, I haven't changed anything there. Last week I pushed up number 5 and the hints unlocked. I also pushed up 6 and the hints unlocked. I'll spend some time today, if you want, looking at set number 5, but I also want to start looking at set number 6, which will be due the Friday, next Friday. It'll be due after the take-home exam has been posted, and some of the content from set number 6 is definitely on exam number 2. I'll just hold off posting the solutions for that probably until Saturday morning. But it'll be up and running, and when we leave class today, a lot of set number 6 material will be underway, and I'll wrap up on set numbers on chapter 5 and of course set number 6 at that time next week. One other thing before I look at the projects area, I've added some things under other course materials. I've added an exam 2 example problems, and I've also added a final exam review, which was for fall 2018. I'll update that for 2024, but I think it's going to be very, very similar. So this exam 2 example problems is in lieu of me giving out an old exam, because I just don't typically do that. But there are some example problems here in this link, and there are things to help you. This is what you've already turned in for problem set number 4, but this just gives you an example of the types of things that I've asked you about doing. So there's a couple problems in there. These are just typical of what might be on exam 2. And then new material is minimum phase systems and all-pass systems and linear phase systems. So this stuff will become more relevant as we get to looking at it in chapter 5. It's already up there though, so you can put it somewhere where you can grab it, or just know that it's on the website. You know, you might say, why is Dr. Wickert so preemptive? It's because I'm busy like you are, and you get running along and you say, oh, I have to do that, and oh, that's messed up, and you probably don't have any idea how many times I post a page and then I go look and it's like I missed something, I didn't change something, it's still old junk from the time before, and I'm trying to stay on top of that as much as I possibly can. So I'm not going to leave this page up here, but it is up there, and like I said, the review sheet is pretty good. It'll, like I said, get revised, and the strategy for this when the time comes, which will be the Wednesday before finals week, I will go through this and redline, write comments and other things on it, and things relating to what's on the final exam. Like the FFT is the final topic we'll be looking at, and so I have a little bit more detail on that in this particular review sheet.
So exam 2 doesn't have any Python on it? It's kind of more like a...
It will have Python on it, yeah, definitely, because you've got it, and I want you to, there's a couple of few problems that would be the regular work out the answer, but you can check with Python. Then there's some things that I specifically say, do this and do this in Python and check this out. And it's all done for good reason. I mean, it's not to make, it's to make it satisfying is what I'm interested in, making you do something and say, hey, this does really work. And of course, it's a take-home, so you can always use the tools that you have to use. But I point you in that direction. So yeah, I take advantage of that fact a lot. So I just want to re-emphasize my wireless mouse does not want to work today, so I'm using the trackpad, which is, my fingers are finally getting warmer because I did ride my bike, but let's just start by looking at this again. 2 weeks ago, I tried to give you a kickstart on the project, and I'm going to do a little bit of that again today, but in a different part of the project. So this top part is all final. I mean, we looked at problems 1 and 2, and if you haven't started on 1 and 2, get on problems 1 and 2. Problem number 3 has been omitted. I've actually been working really hard on adding more features to Scikit DSP-COM, and they were motivated by what I originally wrote down here for problem number 3 with the FPGA and the accumulator and numerically controlled oscillator. But then I've gone way beyond that, so I might craft the final project from some of that stuff that I'm working on, and I'm wanting to get it pushed into Scikit DSP-COM so that you can just upgrade your system with the newest version. But for the time being, it's totally gone. I just left it in here kind of as a reminder. We are going to be looking at the Pi Audio helper problems here, probably next. But something I didn't point out to you 2 weeks ago is when you get to the very bottom of this project 1, I have references, just probably more for me than for you, but I forgot to point out that there's a whole set of comments on here, basically hints to go along for the project problem. So I went through them on the video, but I had forgotten that all of this was already in place. The advantages of being old and having done this so many times, it's like I kept having to do certain things, and eventually I just said, I'm going to throw it all out at once, so that way you don't have to go collect it up. It's at the back of the document. So for number 1 and 2, pretty good discussion on things that we've already had in class that you can watch on the video, but a little bit more detail here on number 2 about techniques of how to figure out theoretically where the alias frequencies are. So I kind of have a little bit more of a discussion in here, and you might remember this from 2 weeks ago when I ran the simulation in Python and upsampled and didn't have the interpolation filter. We saw these pairs of things. I'm wanting you to verify that they are where they're supposed to be, and then use the find peaks function to find them. But I kind of give you some ideas on that too. And number 3, I just simply re-edited it this morning and did a strike through, so it's clearly not even present. And this is the point assignments. For number 3, it says polyphase decimator. That was thrown out, but you just have to look at the bottom line in this points area and just know that the 40 points that you see in here for problem number 3 is just gone, so this will be 40 points less on its total. Does that make sense?
I have a question, Doctor. Are these like combining, like problem 1 goes on to problem 2, goes on to 3, 4, or 5, or is it just completely different steps?
They're different problems. Yeah, they're all kind of different topics. The first one is to get into programming. That's a good question, though. Method to my madness. It's evolved over many years, though, of having a project, having things in. I was looking at my history, all my files and stuff of how I kept something around for a year, and then I removed it, then I put something new in, and then I enhanced it. I mean, it's just like a whole, it's a playbook. If somebody's to write a biography on how I taught this class over the years, it'd be an interesting study. probably some of the things I did in the very beginning were really good and I could bring back again, but I'm just staying with where I'm at right now. I feel comfortable with it, and I'll just tell you as a testimony from students, people have said this has been hard work, but they've said it's been very, very good. People have really given me positive feedback about what they've learned from doing these projects. So I look at them now and I try to think about how are you feeling about it, which is the reason why I easily said, let me just get rid of problem 3, because you've got enough stuff to do. And of course, the students, like you, would always say that. We have so much to do, you know, across our spectrum. But I have these things and pet peeves, and because I work in this area and I'm working really hard and doing things right now on this project for the company, I just cover the waterfront with DSP as the core, and then statistical signal processing is kind of what I'm into right now. Has everybody heard the term data science before? So I'm using a data science approach in something that I have to do right now, where I have to try to estimate some probabilities, and I don't know exactly what the density functions look like, and theoretically I could analyze going through the math models, and I have some papers on this subject, but my implementation is just a little bit different in how it's going to be put into FPGA. So I said, why don't I take the data science approach? And this is interesting probably to you too. Data science has to do with just having a lot of data, or in some cases, before the data science term maybe was popular, another term was around called big data. You remember that? We went through big data. Well, I don't know what big data means to you, but I know what it means to me. I go anywhere, and within a matter of hours, if I go to UC Health, like I had an MRI done yesterday as a follow-up, or anything, what's happening in your email a matter of moments later. Please tell us how we did. Please fill out this survey. Don't you guys get that all the time? I go to Einstein Bagels on Saturday mornings to buy some food for our family, and what are they sending me? Because I'm a member of their club, to get some points so I can get a free box of bagels every now and then. They want to know. Everybody wants to know, and that's part of the big data craziness. They collect all this stuff, and then a data science engineer, software kind of person, takes all this data and rambles through it and tries to draw conclusions out of it. And of course, we just finished up elections last week, so there were lots of surveys going on that. They weren't just asking for money, they were asking for, will you vote for me, or do you like this or don't like this? So the data science idea, though, is really been true in signal processing all along, but so I'm going to generate ensembles of statistics, kind of like ensembles in a random process, and then I'm going to use some of the cool statistics functions that are available in Python and in Julia, but I'm using Python at this work, but there's a function called PDF fit. So if you have a bunch of data and you think it's going to follow, like for me, it's maybe a central or non-central chi-squared PDF, which is formed when you take the sum of squares of Gaussian or normal random variables, either with zero mean or non-zero mean. It becomes this PDF. Of course, if you take more and more samples, everything tends from something you learned about the central limit theorem. Remember that? What does everything tend to when you collect enough of something? In many cases, pardon me?
Is it like move towards the mean?
Well, it moves towards a mean, but a distribution, rather than being uniform or Rayleigh or anything else, it'll tend towards a Gaussian PDF, a normal type PDF. And the term normal was Gauss's way of saying, you know, this is the normal PDF, as in, you know, the one that we always find is around. That just shows you how slang and generalizations haven't changed over the centuries, actually, because he made that discovery a long time ago. And I think it's funny because the term normal is something we would use, right? Oh, it's normal to get sick this time of the year, or anytime we use that word normal, it's like, what does it really mean? And so when you think of a PDF called the normal PDF, which is the label in Python, it goes back historically when that term was coined. At any rate, so I collect all these statistics, and then I can fit a PDF to some measurement data. So I'm generating my own data, whereas in data science, they generally get the data from some collection, surveys, and other things that are done in whatever the field happens to be, medicine, business, so on and so forth. So I'm doing that right now, and that's just working over here. I work here. I mean, it's all still kind of in the same realm. So to me, it's a lot of fun. Is what I say.
Doctor, what would be like the final format of this project submission to you?
It would be very much like what you might do in the Python versions of the homework. My intent would be that you would publish your, I'm giving you 2 notebooks to write in, and let me just thank you for the segue, because now we can go right over here and just look. I've given you 2 notebooks. I call it Project 1 Sample. These are the ones that I cleaned up last night. So this one covers problem 1, so it gives you a place to do your work. It's basically right in here, where I say write code here, and then you do experiments with it. And the problem experiments are actually right in here. These are from the project reader, but it says run this case and then run this case. So you'll do that right here in the notebook. You'll have the plots, and then I'll grade off of that. Problem 2, similarly, I don't detail out as much, but it's just going to be a flow, parts A, B, C, and D. Problem 3, is gone. I just say in here now, a variation may be in the final project, but I don't have any guarantees on anything. Problem 4 is very straightforward. It's probably the most straightforward of the entire project. We can look at it more today if you want to, but it's about a notch filter and doing some measurements on the notch filter. And I do have hints on it, and it comes to mind this time of year that this might be a question you'll have, but I can't second guess what you're going to ask for in terms of I don't understand, but I have a good idea that this will have you a little bit thrown for a loop until I maybe say some more, and I think that's why the comments are in the back. I think I've tried to head that off, but I'll say more. Problem 5 is all on PyAudio Helper, and it's actually in its own notebook, so it's right over here. It has everything in it that you need, and included in this are files. So if I was to go into here, let's see, I think it's a folder in here. No, it's got to be one level up. When you unpack the zip, you're going to have this layout of files. The only thing you're going to be different on is when you first unpack it, you won't have this file, and it's because it's on a separate link, because remember the file size issue. So I download that one, and then I would move it into this folder, just so it's all together. So this is the one that's the most exotic, off the beaten path. It's more like a lab, and absolutely a lab, because it's real-time DSP. It's something happening in real time. So as I've already said at the start of class, you will want to make sure that IPy widgets are on your system, because they get loaded in, and I give them the alias name of just widgets, and what will happen is when you try to load something here in this setup, you'll see that it says widgets do not exist. So I had to do this last night on this computer because I hadn't put them on. That was, if you don't remember when I said this, but it's over here. That guy right there. That's what give you the sliders and GUI elements that you'll be programming to. So back into this, I run this cell, which I've already done. It loads in stuff. Pi Audio Helper used to be part of the package for Scikit. It's now in a separate area on GitHub, but it doesn't work, and we have to get it rebuilt. But right now I've included that in here. So you've got a file called Pi Audio Helper Old sitting right down here that you can use with Python 3.9. It will not work with Python 10 or anything like that. It's stuck back at 3.9. So this we talked about weeks ago. What, let me move this back over here. Maybe even turn that off. What goes on with the audio subsystem. I went through this one day and we got it up and running. I'm going to go through it again. When you first get up, I've got a series of steps in here, and these steps are for your benefit. When I wrote my Signals and Systems for Dummies book, and I had editors from John Wiley that were pounding on me, they were saying, what is philosophy of dummies? We want to lay everything out in steps so people know they have no step 1, step 2. So whether or not I'm stealing an idea from them, I don't think steps is a new thing, right? Whether you're cooking, whether you're baking. I mean, I like to bake stuff. I pull recipes off the internet, and I want to follow the steps, and I want to see what, I know there's got to be a step here that says what is the temperature your oven needs to be set to and how long do you have to bake it. And if you have to use a probe for your meat, let's say, to see if it's up to temperature, I'm giving you those types of steps. I don't know what else to say other than steps are important. So, and this is an example that runs. I've got another example in here that already runs and gives you a lot of details to help you with the parts to problem number 5. So step 0 is to see what devices are on your system. And so you run available devices. And in this particular case, when I came in here this morning, I didn't have my Beats headset plugged into my device, and I had some indices used over here to tell me what index is going to be my input device, which one's going to be the output, and then it got screwed up. So this file, as it's stored in the zip, is not going to look like this because you won't see a Beats headset, because that was just brought on my system today. Now that brings up a good point, though. If you have your system up and you have your notebook initialized with that first cell, and then you plug something in or unplug something, this list is going to change, and your program might not work. You might have to reset the notebook and make sure the devices are correct, because it's kind of a dynamic thing.
So don't plug anything after.
Yeah, or just the old adage in software is, what do you do if it doesn't work? I reboot or I restart something, restart the notebook again, which for me, this is what I like to do, restart the kernel. And then everything has to be run again all the way through. And I generally just run one cell at a time. So here, just to go through the philosophy on this, I want to have an input come from the onboard audio. I don't want to interfere with Beats Flex because I'm using it to record on my screencasting. So I definitely don't want to be interfacing to it. But Realtek is very popular on a lot of PCs, so I'm looking for Realtek devices. So Realtek microphone, 4-channel. Okay, that's going to be my input. So index 1, I'm going to make note of that. And then I see speakers to play back there. Maybe I'll try Extron, Scalar, whatever it is. That's the interface system that I plugged into through HDMI. Most of you probably have an HDMI TV and know that you can get audio through a different device. I might try that because I couldn't get it to work, but now I see it has a device index here of 6. And there's a volume over here, so maybe I'll make a big sound rather than on my PC. But I'm going to go with 1 and 5 initially. So that's just kind of like a catalog to know what I have to get. The next thing is, for all these problems, is you're going to be creating a GUI. So here I create the GUI. In this case, for this demo to play this audio test file, I'm creating a left gain slider and a right gain slider. This goes through all the orientations. You can change parameters in here. I think they're pretty much self-explanatory. basically they go something like, what is the value? And value is what you read into your software. So if I put 1.0 in there, that means that's how it's going to initialize when I first create the GUI. And then min and max, pretty self-explanatory. Step, when you move the slider up and down, what is the smallest step? And I think I told you before, if you're wanting to see your widgets immediately, you can uncomment this, and then you will just see the widgets all by themselves. They're not going to do anything, but they'll be interactive and they'll be useful. I don't want them displayed here because I'm going to display them after I run the real-time code. So this is the callback, and I'm going to go into more detail on this in the second example that I've got here, which goes specifically for one of the parts of the project. This one that I'm looking at right here is just something I think you should go through to see if your system works. Just use it as a test bench. Is my system working? This one doesn't do anything except take data from a buffer, a circular buffer, rather than from the input data, because we're not actually going to take data signals in from a microphone. We're going to use pre-recorded data that I'm giving you. So I'm mimicking that using this object from buffer, and that's, again, learning about how that works by example. All I'm going to do, though, is I grab samples from it in stereo fashion, not always stereo, but in this case stereo. I'm going to gain scale them to be integers that are around 20,000 for its amplitude, because it's a 16-bit signed integer, and grab a new frame from the array, and then the only DSP I'm doing on this is multiplying those values, these buffers, x left, x right, by the slider value, left and right gain slider. And all of those variables are brought in as globals. So I have to bring in the basic DSP IO object, I bring in the left and right sliders, and then in this case I bring in another object, which is my audio stream that I'm just looping on. I have to compile this cell, of course, so compile it by doing Shift-Enter. And now we're down to the heart of the matter. We're going to bring in a test vector. I'm going to put it into this object, loop audio class, and it's going to create this instance of the class called xLoopStereo, which is used up above in the callback. And then to get the DSP-IO pumping away, I have to tell it what is the callback function that it's supposed to run. In this case, it has a real unique name, pun intended, callback. I mean, you can make it more useful in like callback part B or something like that. But and then the next variables, and of course you can always go inside these guys and do a shift tab, and you can see what are we looking for. We're looking for input index, output index. The rest of them pretty much stay the same. So those variables aren't typically used. T-capture of 0 just means it runs forever. And now I'm going to launch it here with the interactive stream, and this is another opportunity to set some attributes, like if you wanted to capture a stream for only 2 seconds, you could put a value in there, but if you put 0 in there, it will capture indefinitely, and that's talked about right down in here. And if you put in number of channels 2, in this case it's so I can do stereo. Everything else except for one of the problems is going to be mono, so you'll be putting 1 in there. But there's examples of that. So now I run this, and oops, I haven't compiled it. And it's not playing. It was playing moments ago. What did I change? I tried to get it to play elsewhere. Let's just see. It's supposed to be playing on my speakers, but why isn't it playing? We've got too many devices on. I mean, these things can play back. You can play back through the console here. It was screaming at me, though, and I turned the volume way up so it'd be nice and loud. So, and frequently in Pi Audio Help you don't get error messages, so I'm just going to essentially reboot right here just to see if this resolves the problem. And because I'm using my trackpad, I'm not doing great there. Okay, reboot it, restart my kernel, make sure I run this cell, and okay, it's done. Check out my devices. It looks like audio input is still on 1, and 4 is the output. No. Yeah, 4 is the output. I think that's what I was doing, but you know, I could have messed that up too. Rebuild my widgets. Do that. Oops, I had it on 5. Wanted it on 4, right? What's that?
That is pretty cool.
Now, let's see. Should I go for broke here? Let's go back up, because you're going to fiddle around like this. I know you will. So let's just try this and just see if this Xton, whatever it's called, scalar, that is on 6. See, I was sending it to the wrong one. I sent it to 4. Let's send it to 6 and see what happens. So I'll go down here. I'm going to send it to device 6. Recompile it. Run it. It is working. Is the stereo working? Is it going from side to side?
Yeah.
Okay. Cool. See, this is fun. I don't know if you like it or not, but I love it. It's like I get to, because I play music, I guess I like having something that I can hear or touch. Okay, so that one is done. And you're going to do one with a linear chirp class. So you're going to create a GUI that kind of looks like this, and I give you some hints at it by showing you what it's going to look like. It's going to have 6 sliders in it, and then you can practice with that object here. That's just creating a linear chirp and frequency, and this is the class itself. I'm not really going to run this one, but so here I'm going to create an instance of that linear chirp, and all it does is create a ramp that goes from 0, let's see, 0 to 2 pi. So what you have to do to get a waveform out of it, when you're wanting to get a waveform out of it, you have to take its generate output and pass rapid cosine around it. So it converts something that's ramping to 0 pi, 0 to 2 pi, and over again to a cosine, so it'll create actually a sine wave or a cosine wave. So here I'm just playing with some of the variables in it, and then here I'm going to generate the actual output and run it into the spectrum function, which gives us a plot of, and for those of you that had 2610 here at UCCS, Signals and Systems 1, this is a function that you use, but maybe you've done a spectrogram somewhere in your life. It's a plot of time or frequency versus time. So this is just a chirp. It's chirping up from 2K to 3K, then it jumps back, so it's kind of like a police siren. This is the only problem that when you listen to it might drive you or your family crazy, because you're going to be doing some different interesting things and the sliders that are going to change the rate. Here's just a jump in frequency. So this one is fun though, and you get to use Python as an object-oriented programming environment too. And I've just pre-built the class. The class is right here, and then the generate function, and then some of the other functions that go with that class are called methods in object-oriented programming for setting things. The next problem, though, is the one I want to spend a little bit of time drilling onto. And that is 5B. It looks like I have some of the widgets already created for 5A, which is the chirp right here. And if you think I'm going out on a limb, I've been using this for quite a number of years, and people just do wonderful on it. I mean, if you can't get over the initial start phase, that's when I'm not happy. So the second one is this, and this one is a speech with noise, and the idea is to try to mitigate additive noise in speech. And so I have this model over here which says we have male speech, and I have that in one of the test vectors, and then we're going to add some white Gaussian noise to it. It's a random process. And then we're going to filter it with a low-pass filter, which you're going to make be adjustable in cutoff frequency. And then you're going to listen to it, and you're going to decide what is the best thing to do to get the most intelligibility out of the speech. It's a very relative thing, but I just want you to play around with it. So to kick that off, I built a somewhat more complicated example where I said I'm going to, rather than use a low-pass filter, I'm going to use a band-pass filter. So I'm going to have a filter that can have a bandwidth to it, and I can move it up in frequency or down in frequency when the noise is added, and try to adjust the bandwidth of the filter on the fly and its center frequency on the fly, and see what gives me the most intelligibility. This happens to be a filter that gets designed in the real-time DSP lab, so I just have its math worked out here. Here I define a function which is just going to design the filter. I mean, we're used to the idea that we get B and A coefficients for L filter, and this just says what's the center frequency, what's the bandwidth, delta F, and what sampling rate do I want. So now I set up a bunch of widgets. When you do the problem, you're going to do something different, but this is just to give you an example. I'm going to set up, and you'll be able to reuse parts of this. I set up a gain slider, just the overall amplitude. I set up one that adds the noise in, so I can change the signal-to-noise ratio on the speech. And then I have another one to change the center frequency and the bandwidth. So I run those widgets. And just to see what the filter looks like, I'm going to do a pole zero plot of it, but this also has a very important step in it. I'm going to import the speech vector right here. I think I import it again later, but the most important thing that's in here is I design an initial bandpass filter, and then I also use this function we talked about a few weeks back to create an initial condition vector that I can feed in as I'm looping in real time, because this is an example where we need to filter with an initial condition getting passed back in every time we filter one frame through the Pi audio subsystem, which is built on top of the PC's audio subsystem. So that is handled right here. So it gets created right here, along with creating a pole zero plot of the filter. This is going to be better understood when we get into Chapter 5, so I'm not going to dwell on it. I go ahead and plot the frequency response right here. I think I imported this at the top, but I'll do it again. There's the response of the filter for its current settings. It's set on 1 kilohertz, and whatever the center bandwidth was, I set at 100 hertz. You can see that right in here. This is the center frequency, and that's the bandwidth of it right there. And those will be controlled by sliders. So now what does the callback look like? I'm going to bring in the gain slider, I'm going to bring in the DSP IO and the loop buffer so I can take the speech and just keep circulating it around. I'm going to bring in a gain buffer and standard deviation of the noise that's going to put additive noise in. I guess I bring in the signal to noise ratio, and then I bring in a GUI slider for the center frequency, the bandwidth, and also the coefficients of the filter, and also the initial conditions of the filter, so that every time this callback is run, these things can load back in again so that it doesn't lose its mind. It's kind of like this callback is relying on certain global variables to be present so that it can signal process the signal coming through. But when I go away from the callback and come back again, I need to restore those to make sure I don't lose them. So the heart of the matter here is that I'm getting samples. In this case, it's mono, just one channel of audio. And I'm scaling, in this case, by 32,767, and that's because it's a speech vector that is designed for 16-bit audio, and I just want to restore it back to its original scaled value. That's 2 to the 15th minus 1, if it looks familiar to you. And then I'm going to add in, there's a plus equals here, noise, and that's going to be set by the SNR, and then I'm doing it in amplitude, so I'm dividing by 20 to go from decibels back to a linear value, and I'm going to set the standard deviation on effectively this noise vector that I'm playing through and generating right here, rand n. And then I design the filter on the fly according to the values that come in from the gain slider, and then I'm going to filter it. And this is the heart of the real-time DSP. This is where the signal samples that come in X, which have had noise added onto them, get filtered. And each time I filter it, I have to take the initial or the final state out of here and bring it back, and I have to put it in, and then I capture it again. It's a global, so I can bring it back in again to push into here, so I have continuity. If I was to ignore that, I'd have clicking and other obnoxious things happening because I would not have those initial conditions maintained. So run that. And we were using, just now, we were using one, it was 6, right? That was the output to get out of here? Yeah, so let me do that.
The sockets in the wall still green. The child crawled into the dense grass. Rise failed where honest men work. Trampled the sparks, till the flames with the spray. The hilt of the sword was carved with
Maybe before I do that, I'll just let you hear.
a round
Here's the bandwidth.
through the thin forest. Footprints showed
That sounds more natural because I'm not filtering the speech with a bandpass filter.
he was waiting at my front lawn. Events near the edge.
This is the bandwidth.
Prod the old mule with a crooked stick. The sockets in the wall still green.
So the idea here is you,
Rise failed where honest men work.
Like they were doing that in the early 50s and 60s on radio.
what, filtering?
Yeah.
We have to think for a male, our vocal cords are lower pitched than a female, so I would think it'd be fairly low, and the noise is covering everything because it's white noise, so you want to kind of get your filter centered around the most important parts of the human voice there, and then set the bandwidth accordingly. It's subjective, though. Interesting. I mean, I like it. So, is there one answer that's correct? No, but you're going to just, say what you think, and you're going to try to convince me that it actually did work for you when you do the low-pass filter alone, which is not quite as complicated. So, here's the framework for that one to get you started. Same 8K speech vector. This is from open source files that are out there. There's a huge collection of speech vectors, and I got involved with this years ago with audio codec testing for cell phones, and so you have, my favorites are male, American female, British male, and there's children, and all kinds of other things out there, but I use those in a COM1 systems project, so you have different, you're transmitting signals that have different speech files going through them in a loop. So there's your callback that you're going to do. So I'm leaving a space in there for that. The final part of problem 5 is jamming, and here I give you a test vector that's got two sinusoidal tones jamming the same male speech, and that's already pre-built. The tones have already been added, so you're just going to bring in a single file here, and you don't know where those frequencies are. You're going to set up 2 notch filters, and you study this type of notch filter in problem number 4. So you get familiar with that in problem number 4. So there is some continuity from problem to problem in this case. Again, we're running at 8 kilohertz because it's 8 kilohertz speech. And then you're going to set up programmability on that notch filter and sliders and so on. I make this problem really easy in terms of the filter because I have a function in here that's part of the SIG-SYS modules. It's called FIR IIR notch. So this is very useful. It defines the filter. You get to put in the center frequency, the sampling rate, the pole radius, and once you work problem number 4, you'll understand more about what these attributes are because you'll be studying it in more mathematical detail. It returns the coefficients, and that way you can use that. You will utilize that in here, kind of like I just showed you for the speech with noise, and then you will run it and look at the response of your filter, and I encourage you to go ahead and look at the spectral peaks to see where the jamming signal is, because that can actually tell you where you have to set the notches at too. But it's fun to just do it blindly, just be listening, moving the slider up and down until you hear one signal notched out and then the other one goes away. And you could think of that as being somebody jamming your channel, maybe not your radio channel that you listen to music on, but it could be somebody jamming the missile that's flying into its target or something like that. Do you have any immediate questions? Okay. Go for it is what I'm saying. And just persist, and I'll be expecting more discussion on it, and we can talk about things. We can do a Slack. We have the ability in Slack to do the call, the huddle, if we want to. I don't have it running at this moment, but if you talk to me and I'm available and I want to engage you right at that moment because you are ready to talk on it, this is how the huddle starts up. So if we're on a channel, if I'm on the channel with any one of you and I say, let's do a huddle, I will say so, and then I will click that, or you could click that, and then all of a sudden the window's going to open up and your whole screen's going to share. You can share your screen, you can just talk, you can do whatever you want to with the huddle. The only thing you can't do is huddle with more than one other person because the free version doesn't give you that ability. The huddle idea would be if it's like what I do on Teams all the time, is every morning we have a Teams call, which is the same idea, though, as this huddle, and it's like 5 of us or 6 of us. The managers are going to give me a status report. What have you done today? What's the biggest thing management wants to know is, do you have a blocker, right? Have you, both of you, heard of that term, blocker? Like, is something blocking you from making progress in your work? They want to know that because they want you to get that resolved so you're not sitting around doing nothing. And let's see, yeah, somebody messaged back to me, but I'm not going to look at it now. So let's finally move on to some notes. I will want to go back and look at something in quantization from Chapter 4, and then just to let you know, there is, let's see, thought I had this opened up before class, yeah. There's a nice Chapter 5. This is still the 2022 version, and I will update it as I see fit. I'll probably try to get that pushed out there so it has the right year on it. But it goes through all the stuff that's going on in Chapter 5, and of course over here in 4. I kept tapping the wrong thing, so I brought up all these launchers. But Chapter 4, I just want to go look a little bit at quantization, because that's problem 3 in the homework that's due right now. So let's go over to the notes, though, and just see where I was at with that. So this was one of the last things we did before we left to, last week on the video. We were looking at, no, is that right? No, this was done 2 weeks ago. Last week was random processes and everything, where I got to lecture to myself for all that time. So we were doing this model for quantization noise based on our random process ideas. Actually, this was covered last, was it? I'm confused now. What did I do last week? No, this was done last week. Quantization noise. Because right after this is where we go into the topic for today. So the additive noise model says that when we have an A to D converter that has a finite number of bits in it, we model a signal as being a quantized version of the input. So it can be x hat, or it can be q of x of n, depending upon how you want to model it. And our simple model is to say that it's just adding a uniformly distributed random variable or random process to our signal to represent the quantization error that goes on with the quantizer. And that was, talked about further back, where we generally think of in a 2's complement format, we're talking about, say, a rounding quantizer like this. So it has this stair step, and values get quantized to those stair steps. You have one less stair step on the positive side than on the negative side, and that's because with a rounding quantizer, you always have a stair step at 0. You want to have a quantization value at 0. So you have, because you have words that are powers of 2 in length, like 16 bits, for example, so you've got one stair step less on the positive side. And that was talked about in here. This is an example of quantizing. The sampler in the A to D would go to the solid value, but the quantizer would go to the nearest stair step with that value. So quantization noise just says, let's come up with this model where we say the noise is uniformly distributed between plus and minus 1/2 stair step, and a stair step is delta, and that's 2 to the minus b over xm. And remember here, the book uses b as the number of bits for the magnitude. The sign is the extra bit. So b is 1 bit less. If it was a 16-bit quantizer, b would be 15. So I went through creating some pictures of that in here. to try to prove to you that it's a fairly reasonable model. As the number of bits gets large, it doesn't look that far off from, say, a actual simulation with quantization. And you can put together a nice theoretical model then, and that's what you do in problem number 3, where you're basically using this formulation right here, which says the signal to quantization noise ratio in dB is equal to sigma x squared over sigma e squared, and sigma e squared is the fixed value given by the parameters of the quantizer, and that comes about from over here, where you have x max is the full-scale dynamic range positive, and then minus x max negative. So one of the things that comes at you when you have to work this problem is you have to find the variance of the signal, and if it's a deterministic sinusoid, sigma x squared is just the power in the sinusoid, and that's something that you actually know. It's just a squared over 2. We assume a 1 ohm system. So that can get brought in easily, and I had this example that I went through last time saying, on the video that is, saying that suppose you had a signal that was normally distributed, zero mean and sigma x was its standard deviation. You might want to set x max so that you rarely exceed the threshold or start clipping or have overflow. So let's set it up so that we use a plus and minus 3 sigma window to set x max. So when you do that, it says it only exceeds 0.27% of the time for a normal random variable. And when you set up your quantizer on that basis and plug into the equations, you get, with a 16 total bits, 15 bits for B, that you get signal to quantization noise ratio of 91.3 dB. And I don't know if any of this sticks in your head from your personal listening to music, but when the compact disc player came out, it's 16-bit digital audio, and people said, oh, you're going to get 96 dB. You don't really get that unless the signal is perfect, signal to quantization noise ratio, unless your signal is perfectly matched to the dynamic range of the system. So 96 would be for a single sinusoid being run pretty much right to the rail, where it's just on the verge of clipping. I thought I had an example in here of that. Maybe I don't have that number written down, but this is a more realistic number. So what do I have over here in the simulation side of this that you can use to compare? And in the homework problem, you're just doing a equation-based calculation. Very likely in exam 2, you're going to be doing a simulation of this. So I'm hinting at that strongly, and I'm saying, hey, you're going to take it to the next step of actually measuring it. So I have a quantizer defined in scikit-DSP.com called simple quant, and you get to specify how many bits total, what x max is, and then what type of limiting you want, whether you want it to be saturation, which just clips, or overflow, which a 2's complement number does. When it hits the ceiling, it rolls around, or none, just ignore it, but just know that that's the quantization level you want. So, and it's a simulated version and can be compared against this theoretical model, the additive quantization noise model that is in the notes and in the book. So I kind of review, the math right here is just a review of what's already in the notes. So here, I just took an example of a sinusoid, and I set the number of bits to 5. I set the amplitude. I have to remember, so I always go Shift-Tab, remember what it is. The third argument is x max. So here, this is an amplitude 1 sinusoid. So right now, I don't quite have enough dynamic range to handle it. If I was to set threshold, X max to say 1.2, and now I get an extra 0 showing up over here, 5 bits. Now I can represent the plus and minus 0.95, but if I suppose I bring this value down to 0.9, now we'd expect that, we're trying to go over, so if I put, instead of none in there, I put saturate in there, it's definitely taking the top off of it, right? But a more likely condition that will exist would be the third argument, or the overflow. So this is what 2's complement would do. What did I do wrong? Put the wrong argument in there, or did I spelled it right. Okay, what did I do wrong?
You don't take a break yet?
No. I can't talk to you right now because I'm lecturing. So overflow, let's go back to saturation. Okay. Oh, it's over. I can't read my own notes. Over. So now what happens when it hits the top, rather than clipping, it just simply does a 2's complement overflow, and this is what you'd expect. It's reaching the saturation or the overflow point, and then it changes sign, and then you see a little bit of the sinusoid in there. You may have seen this playing with microcontrollers. Has anybody ever seen this on a microcontroller where you overflow numbers? If I increase the number of bits in here, this is a very small value just so you can see the stair steps, but suppose I make that 10 bits. You see that type of thing when you're overflowing on a 2's complement number. This doesn't have to be in an A to D, it can be just fixed point arithmetic on a computer, right? If you were doing it in a microcontroller like signed integers of 16 bits. So you want to avoid that at all costs. So generally what I would do is if it has to be normalized to 1, what I have to do is go over into here and set this to 0.95 times that. So now we're fine. There is quantization noise in here, though, and if I was to go look at the spectrum, which I guess I have an example right here. I don't even know what this example is. Well, this is a theoretical calculation of quantization noise, but let's just take an example where I actually run. SNRQ has to be defined. So here, this is the additive quantization noise model, and I'm not looking at the absolute amplitudes. I'm actually got a new version of a function for spectrum that I've been working on to put into the package that scales differently, but still you can see that the noise floor from the additive quantization noise model is right down there somewhere. I mean, I have to scale it better. I'm not really focusing on that too much, but then I take the actual value from simple quant at 14 bits, and they're pretty much the same. They're not exact, but this would be the real quantizer scenario where I'm quantizing the numbers using the model, using using a numerical model that would show up in fixed point arithmetic, and then the additive noise model is down below. So like I've already said, I'll probably have you drill in on this in the exam too. Just study it in more detail. This is just a quick hack at it, not getting it too exact. And if I can get these new functions put in there, then you'll have that too, rather than the other way. But I've done problems like this before, and again, this is pretty satisfying. Simple quant is very handy to use if you're wanting to do fixed point modeling, but the additive noise model has been around for the longest time, and it also is a very easy thing to calculate with pencil and paper, and that's what problem 3 is having you do. Just to review again, since I didn't bring that up. And here, I'm giving you this type of quantizer, 24 bits total, so 23 sign bits, so B is 23 in this problem. X max is plus and minus 2, and I put the sinusoid amplitude at 0.9, so 0.9 doesn't even need to be an issue because I can go all the way up to just shy of plus 2. I'm one quantization level less than 2 in signed arithmetic, but there's going to be no overflow. There'd be no saturation if you were in that mode. But in this problem, you're not doing any simulation with it. You're just simply doing the hand calculation. What I was starting to point at in the Python now was what you might have to do on exam 2. And I'll just, in any of this, I'm going to hold your hand on it with the problem. I'm going to say, do this, do this, do this, and then you'll get to see, have an idea of that. Again, it's good stuff. It might be an A to D. It might be just an algorithm interior to some system where you've got to worry about fixed point arithmetic. And we'll study more of that in one of the last chapters of the book, which shows up, it shows up in chapter 6, topologies and then some fixed point issues. I'm confronted with it in my work right now. I'm modeling in the luxury of double precision float. I do have some fixed point somewhere, but the guy that's implementing it, who I'm working with now very closely, is doing it in FPGA, and he's got to pick the bit widths that are appropriate for what's available in the FPGA. Bonus problem 4, segue. We're going to go look at that right now. So that just reviewed through the tail end of the lecture from last week. Now, for the bonus problem and a little discussion on that, it will be how do we model the D to A converter when we're coming out of the system. We're going to have to go through, wait a minute. Yeah. We're going to have to handle the precision inside the system, which is some x hat b. So it has, say, 16-bit signed integer. B would be 15. Then you want to scale it by xn to take it back out to an analog value that would be coming out of the D to A converter. And popular values are plus and minus 1, plus and minus 2, or something like that, depending upon how the D to A is set up. And then there'd be a zero-order hold, the converting from the samples to impulses, and then effectively a zero-order hold. So the zero-order hold idea is that the D to A converter, when it's getting clocked and signals are going into it, it will hold the value of the output until the next value comes along. So that's the zero-order hold. We might think of it as impulses interior as a discrete sample, and then it has to wait till the next sample comes along. But in the book and in the way I like to think about it is it's being held by the electronics, the analog electronics. So the zero-order hold is a rectangular pulse of duration t seconds. And it holds the output constant, and it will hold any quantization error that might be present on the signal as part of the input A to D, so that's over in here, or maybe changes in precision in going through the system. Example of that would be maybe you're sampling with a 16-bit converter at the input, but you go with 32 bits interior, or in the case of the real-time DSP lab, it's floating point inside, but it's 16 bits outside. And then before you send it back out to the analog world, you might go out with 10 bits, 16 bits, some value. I mean, so there might be some additional quantization noise, and that's just why there's two terms here. And that made me think of something in Pi Audio Helper, which we went through already. I was scaling by 20,000 in one problem and 32,000 on a speech vector in another problem. That's because the audio subsystem on the PC is based around 16-bit A to D and D to A. So we get to work with floats when we're inside in Python, not a problem, but we can't bring a signal, a test vector in a loop that's running between minus to plus 1 and try to send it to the output where it's going to get converted from float to int 16, because that will do nothing, right? If the value is going to run between plus and minus 1, it's going to be like 1 bit of toggling. So you have to scale it up, and that's why you see some of that scaling going on inside of there. So just be wary of that too. We didn't see that today, but if you don't scale it properly, in my examples you see that scaling, that makes sure that it's actually toggling bits on the D to A converter. Has anybody ever seen that happen before in working with microcontrollers? It's upsetting. Why is it upsetting? Because you can spend a long time figuring out why isn't something working, and then it could be something as silly as I'm not scaling it up to integer ranges. Okay, so what that zero order hold is going to do is it's going to put a sync-like spectrum. This thing is a sync function. This thing's not working well. I can barely draw because the computer is not letting me have control very much of the time because of the video, I think. So sync spectrum. I put an E on there thinking I was trying to say since. I actually don't know what I'm doing right now because I'm all fouled up and I can't write. So a sync spectrum, and there it is, the magnitude of the sync spectrum, and it rolls down to 0 at the sampling rate. So it's halfway down, or part of the way down. It's down 3.9 dB at the folding frequency. So what happens is you have this frequency group, and that's this area in here. And that's the roll-off due to the zero-order hold. What can you do about that? Okay, these guys do not know what they're talking about. You idiots at the Computing Services Help Desk. They supposedly fixed this for me. It didn't fix it. They did something last week. They said it's never going to power down again.
Say that the undergrads can work as partners on the project?
Yeah, you can. Yeah. So we have 2 and 2 in this class. You guys can work together. You have to work alone, and the guy that comes can work alone. So maybe I'll point the computing services handy workers to say, look, it failed again. And was I inactive? I was moving. You guys were moving. My computer was working. I was drawing. I mean, what more can I do? And I told them, I said, this is very aggravating. They said, we're going to do one more step. We're going to keep it from ever powering off, and it's going to be your responsibility to make sure you power it down when you leave. I said, okay. I really think the utilities crew put some crap in there to control energy usage and makes it spike and then shuts it down. I'll never come back and teach in this room ever again in my life. I mean,
Blacklisted room doctor?
yeah, exactly. They don't know what they're doing. I mean, they don't. I mean, there's too many fingers to point. There's people that come into work when they put all this energy-saving stuff in. They messed some wiring up, is what I think they did. We could go up there and bring an extension cord in and put it on an outlet or something and just do our own experiment, but I got other things to do. So we have droop present. So how can we deal with that? And the thing is, if you have a D to A converter, the sigma deltas don't have this problem, and that's what we have on our PCs and the audio systems on the boards that I use. But in the traditional model and in hardware that you develop with in practice, there is still a zero-order hold that's present in certain types of D to A's that are out there, especially the faster ones. So we have to build a compensator, and this is what problem 4 is about. Basically saying we're going to put the inverse in here. So that's in the denominator. So that's going to be 1 over that zero-order hold response just in the passband. So here's the math model for it up here, and here is just a picture of it. The homework problem just takes a slightly different slant on this. It's a bonus problem. It's number 4. It's actually a very easy problem, though. But look at my hint for it, because you have to think in terms of log, and it's not linear. I won't say anything more. Read the hint, though. It's very important. So before we look at sigma deltas and things, I just want to show you what you might do to entertain yourself someday when you have spare time. I went on the internet and I said, DAC with inverse sync. I've worked on projects before where there's an inverse sync capability in the analog output stage of, or actually there's a compensator in the discrete time domain to manage the inverse sync problem. So there's a number of things listed here. Some things I didn't really care about, but this one, equalizing techniques to flatten the DAC frequency response. So it is for real. I didn't make it up or anything like that. So this goes down to all the stuff we've just talked about, and then it proposes at the end something, increasing the update rate. It gives some other ideas, pre-equalizing. So this is probably the idea that problem number 4 is using. You can see it. See if this will. Well, it's not going to work for me today. Last time I did this, I was able to draw on it. At any rate, you can see right down in here, this is what we're talking about, pre-equalizing, so that this, which is inherent in the analog signal chain, gets compensated for in the digital DSP signal chain. Make sense? What would we ever do if we didn't have domains to work in? You know, if we work in DSP, we have the analog designer that gives us something. How do we deal with it? We try to take it into our own hands and pre-equalize it. So now back in here, got to look at my clock. We're winding out the time pretty good. I think what I'm going to do is let us have a break, and then I want to talk about delta sigma, so I want to talk about this. There's no homework problem on this, but I want you to be literate in this topic, a little bit literate. And you're also going to see that a homework problem you worked a while back comes up in the modeling. You remember the feedback problem you had? That's part of the modeling here. So I'm going to put this thing on pause. I don't know if James Tiller is going to come back in, but pause the recording. Okay, we're back up and recording, and
I had a follow-up question for the project, and it only pertains to
you working together?
do we submit two different?
No,
sets, or
no.
just one set with
No,
our name?
no, you submit one.
Okay.
I don't want more than one project to grade, because they're gonna look different and they're the same, so, yeah, it's totally up to you how you want to work it.
And also, I don't think you clarified on, because do you want the code base or the entire notebook?
I want everything.
Okay, so,
I want you to answer the problem if there's extraneous code in cells that you don't think I need to see because it doesn't matter, but don't second guess. I mean, if it's the critical code, like for all of the Pi Audio Helper stuff, that has to be there. Otherwise, if you don't get something to work, I'm not going to be able to see what you were doing wrong, and I won't be able to comment on it. If it's behind-the-scenes stuff in problems 1, 2, and 4, there's really not anything that you can't show. I mean, you have to show everything, because otherwise you won't be able to answer the questions and explain it to me. And that actually makes me think, what was it that I was thinking of on problem number 4, which seems kind of mundane, but it's not entirely mundane. So let's see. One. If I drive this all the way down, I was thinking, what was it that I wrote down here for the hints?
problem 4?
Yeah. The problem that everybody has is this part. I want you to get the transient response, and this ends up being usually is a real stickler for everybody. It's like, I don't know how to do that. I mean, it's kind of like going back to differential equations or difference equations, where we had the force response and the natural response. That's what it comes down to. But you don't have to go down to that level. What you can do, the steady state response you can get for this particular notch filter by just running the sinusoid through and basically capturing the steady state output. And if you want, the other way of thinking of it is when you had a homework problem where you put a sinusoid in, how could you characterize the steady state output? Remember, you had to get the magnitude in the phase at that frequency. So once you have that, you have the steady state response. And then when you simulate this problem from, say, n is equal to 0, you will have the total response, and it will have a transient, and then it will also have the steady state built into it. So if you want to get just the transient response, you can subtract the steady state response, which you already know. So that's what magnitude and phase. So it's going to be total response minus the steady states. And this is a mistype. You will learn just, I don't know what I meant to say there, just the transient part of the problem, and then you'll be able to see it. And you'll see in this particular case, the response decays to 0. So don't get all sweaty about this. You don't have to go back to differential equations. You don't have to go back to all the nitty-gritty stuff. You can simulate it. Just like what I'm doing, I was telling you about data science, right, and how I'm simulating for my current work problem. I decided I can't follow all the details of the paper, and I'm implementing something somewhat different. So it's all the nitty-gritty probability density function stuff. I'm just going to simulate an ensemble in my case, and then learn using this the fitting function that's available will fit a PDF to the data, is what I'm doing. And that's the data science philosophy too, and that's kind of what you're going to do. It's a much simpler problem, but it's still the same idea that you can simulate it. And it's better, though, to just get magnitude and phase, and then you'll have it. I'm going to look at my solution again probably this afternoon if I get a chance, just to make sure that I'm not steering you slightly off axis. There's always that chance, right, because my brain hasn't worked on this for 2 years, but it's along those same lines. So
It does seem overwhelming, Doctor.
yeah, but when you're when you're young, you're moldable and you need to be challenged. Otherwise, you don't develop to be as well tuned as I think you should be. I mean, don't you want your employer to just be so impressed by your ability and how much you already have going for you? And frankly, I mean, speaking is go-getters get noticed. If you're a slouchy type person, you kind of are not going to be as, you're not going to be as noticed. And if that doesn't matter to you, then, that's fine. But that matters to me a lot. I mean, I get paid a lot of money right now, and I could get paid a lot more, but I don't really want to be in that position, because being overpaid is also a bad thing, because that way your burn rate is so much higher, and when the things start to slow down, they're just going to say, well, we've got to cut this person off because we need to save some money. So I don't want to be like that, because I'm old and I don't want to go look for another job. But if you were a younger person and you were really good, you'd probably start demanding more money, and you'd probably get it because they know that you would be able to do the work for them. Okay, so this is an interesting study, and I could spend a lot of time talking about it, so I'm going to try to make it really, really quick. And the idea is, what does oversampling and noise shaping have to do with A to D and D to A conversion? It's the more modern technique of being able to use the delta sigma or sigma delta, whichever order you want to take it in, both the same thing, and oversampling to get better performance without having to use as many bits. So fundamentally, we want to get better performance, and we want to take down the number of bits in the quantizer. Nobody really wants to build a high-order quantizer and have to maintain that precision over temperature and aging. I mean, temperature in particular. A quantizer means you're going to quantize to, say, 24 bits, so that's 2 to the 24th quantization levels. That's a lot of numbers, and if they you think of them stacked up here, they're supposed to be monotonically growing, but you have monotonicity problems where some of the bits may be inverted. The sigma delta just solves a lot of these problems in a more elegant way. So the first thought is, and I'm just going to stick with the pictures, why don't we just oversample a whole lot more than we have, and we can try to overcome some of the limitations. And the thought process goes like this, and this is also true in some signal processing, like with some of the boards that I have, they call it pulse density modulation. So they oversample a lot, and they digitize all in one swoop with a high sampling rate, and then they get bits of resolution from this pulse density. The pulse density idea is only one bit. You just sample like crazy, though, and then you can integrate it back out again to get the variation. So suppose we want to just oversample and then downsample. So this is a random process modeling thing, but it works out with our additive noise model. It works out to say that we're going to effectively, the quantization noise is going to get added in from our B+1 bit converter, but then we're going to low pass filter and decimate back down again. And like I said, I'm just going to look at the pictures, but an interesting thing happens when you look at the impact of that additive noise, and that's way down here. It's the delta squared over 12 is the variance from the uniformly distributed noise, quantization noise, and you get this picture right here. Before you downsample, you have sigma E squared as the noise power variance coming out of the system due to the quantization. When you low pass filter and downsample, this amazing fact occurs. In the band of interest, which is just the downsampled band there, When it's downsampled, it's still minus or plus pi, but it was originally this narrower band. What happens though when you downsample and filter, the noise gets thinner in the sense that it's now sigma e squared over m. So you're getting less quantization noise just by oversampling and downsampling. It's kind of like I was saying with pulse density modulation. You've got so many extra samples, just like when you're thinking of probability and random variables. If I just take more data, I will do better because I will average more numbers, right? Does that make sense intuitively? I'm guessing that you will use that in your life somewhere too. You'll say, more data, that'll do better. I'll just take more experiments and then I'll average what I get and I'll do better. So that's pretty cool. So it says every doubling of m increases the number of bits in your quantization by 1/2. So that's kind of good, but it's not very fast. I mean, 1/2 a bit more effective quantization for every doubling of m means it's still a really hard challenge, but it's heading in the right direction. It's saying oversampling can give you more bits of quantization. And what we're heading for is not b plus 1 bit. We're heading for just simply 1 total bit of quantization. Can we do it with that? And that was the challenge of the sigma delta. So the sigma delta is brings on board the noise shaping idea. So this is the general block diagram. You have a switch capacitor integrator, so this is an analog. You have an A to D converter, which ultimately is going to become 1 bit, but for right now it's B plus 1 bits. Then you have a D to A converter to feed back some of that output with a differencing operation. So that's where the delta sigma comes in. The delta is the difference, and the sigma is the summation of the switch capacitor integrator. If you don't like it, go to the IEEE Solid States Journal and read about delta sigmas from over 10 years ago. Somebody came up with that terminology. It's all about integrated circuit design is what drove this. So when you take this gray shaded block diagram and you convert it to the discrete time domain for modeling purposes in simulation, you have what looks like a homework problem, right? Look familiar? So the accumulator or integrator is just 1 over 1 minus e to the minus 1. Then you have a quantizer. Then you have a feedback. So this just puts in a 1 sample delay because that's needed for realizability, that you would have a 1 sample delay. And then you finally filter and downsample. So again, just focusing on the pictures, this drives it down, the feedback model down a little bit more, saying that if we have quantization noise, we can just represent it, rather than the quantize it, it'll be an additive noise model. So this is now, I think, that's exactly what the homework problem was, wasn't it? I didn't know this at first either. When I first used this book, I gave that problem, and then I said, oh, this was a precursor to delta sigma. So going through all the modeling, and this is pretty much like what you did in the homework problem, it finally comes down to looking like this. When you rearrange it a little bit more, you've got a pathway that brings in your noise, E of n, and it goes through a 1 minus e to the minus 1, which is a high-pass filter. And then the signal path is flat. It's got unity gain in the way this works out. So it just comes through, and this model now doesn't have any quantization noise in it except for the separate path E of n. And then you have the filtering and decimation. So again, focusing on the picture, this is what it looks like. That high-pass filter does this interesting thing of bringing the noise down to really 0 right at DC, and then it's just starting to crawl back up again at pi over m. But when you decimate, that pi over m becomes pi, so effectively this is now what it looks like after you've downsampled. You've got much, much less noise because of the noise shaping idea, the delta sigma. Did it come for free? No, it came with more analog. So we're friendly engineers, right? We have analog counterparts, and we're the DSP side, and then we have the computer side. I mean, we all work together as a team, so they gave us something, and we took advantage of it, or actually a few engineers that were mixed signal people came up with this years ago. So that's pretty cool. And if you go through the rest of the analysis down in here, you're finally looking at what is the bit savings for different oversampling factors. And this decided to die on me. So here, if we go with an oversampling factor of 64, with noise shaping, you're getting about 8 dB, or 8 additional bits is what it's saying. Delta B is delta bits improvement, so you're getting a bit improvement of 8. Not quite good enough, because if you wanted to go with 1 bit, you'd still only be at 9 bits of quantization, and that's not good enough for digital audio or other types of signal processing. So the next thing was to go with higher order noise shaping. So in the model again, it's a double integration with feedback, 2 feedback paths. And that basically is taking this response of the noise, and it's putting a square in there. So it's making it roll off, it's making it a higher order high pass filter. The next step would be to go to P stages, and then you'd have a 2P factor. And all of that means is that it's going to be even more effective at pushing the noise from the baseband out to the edges, and then when you downsample, it all gets thrown away. Does that seem like too good to be true? From a DSP side, we say we'll take it from the analog side. It's harder to build, and it's supposedly far more unstable. And analog circuits, I think all of you have experienced analog circuits that oscillate. True or false? It's pure frustration, isn't it, when it oscillates? And a breadboard is notorious for providing distributed capacitance, which will create oscillators. Has anybody experienced it? That's when you generally end up going to an RF breadboard and laying things out more carefully to keep parasitics down, short wire lengths for parasitic inductance, pads smaller so you have less capacitance and things of that nature. My first job, I got led through that big time because I had a board totally fail, and then we ended up going with a different material and fabricating it on that. It was for a wideband video amplifier, and for optical communications, it had to be a 2 gigahertz bandwidth, and the whole idea was to reduce the capacitance on the interstage amplifiers, and it brings back some really bad memories. I let the draftsman do the PCB design, and when it came back and got fabricated and I was testing it, it was oscillating and being very, very nasty, and my manager got upset with me and he said, you needed to watch this drafting person and basically stand behind them and make sure they made the board properly. So my reward was I had to spend my weekends hand building a breadboard very carefully with some RF breadboard material that we could take in the field to White Sands for testing. And that was my punishment for not watching over. But I was young, and I expected an older person that does PCB design would have known far more than I did. I'm sort of thinking about your experiences. You've learned some things probably the hard way too, I imagine.
I mean, I have to do my own layout and schematics.
Okay. Okay.
So
But
That's all on me.
have you ever found techniques, though, that make it better and things that you never want to do, or you just learned by reading a lot, or?
No, I go through a lot of reviews, so the fellows will be like, oh, before we've had an issue with this, maybe you should look at
Okay,
this
so
example.
tracks that are coupling and parasitics and things like that. It's only gotten worse over the years. It hasn't gotten better, so. That's signal integrity now is the official term for it, I think, right? Okay, so at any rate, with a third order, this is kind of the punchline right here. 64 times oversampling, you can get a delta bit increase of 17.45, so you can get up to greater than 16-bit accuracy, or with 1 bit, you can boost it up by 17.45, so an effective of 18.45. And that's kind of the end of that story. So that it's been around for quite some time now, and you can do the same thing on D to A. Same ideas apply with the noise sampling. And just to look at what you can do, I did a Simulink simulation on this many years ago, but different codecs have been used on different boards. Wolfson Labs from England was a company that was bought by Cirrus Logic, and they have a family of Delta Sigmas. And the board that I've been using most recently, but now it's retired, it's still being used, but they don't make it anymore. It uses a Wolfson. That's what that W is. That's their logo for their audio codec. And this is kind of the way it's laid out on the board. And in the real-time DSP class, the full free credit version, which was taught in the spring, I have them study this schematic a little bit just to see how the various networks in here contribute one way or another. But kind of the bottom line is, when running in one particular mode for a Delta Sigma A to D with the 64 times oversampling, this is what the effective ADC anti-aliasing response is. And you're getting the 16 bits for sure, but you're also getting a built-in anti-aliasing filter. So this is the folding frequency, and it's very flat. It passes through a maybe 6 dB or something right at the folding frequency, but then the rest of this is squashed down, and of course some of this would fold in from aliasing, but it's pretty good. And then this is the D to A side of it, its anti-aliasing response. The droop gets managed by the oversampling, and then you're removing the higher order harmonics. I don't know if that's impressive to you or not, but very perfect looking protection on the input and reconstruction on the output, just by virtue of how flat the passband is. Is that, I mean, it's not crude, it's very, very nice looking, so. And then there's other things out there for RF. There are sigma deltas at RF that Analog Devices has pioneered too, and I got to work with that a little bit for a local company quite a number of years ago. But idea is to try to move the ADC closer to the front end as possible. And TI has some stuff too, Analog Devices, Xilinx has theirs, so I can't keep up with this stuff that's quite a few years old already, but I tried to put in data sheets and stuff just to let you know what keeps happening in these areas for audio and for analog. So audio is far more bits of resolution because it's at much slower sampling rate, but it's more demanding in some senses than RF would be. But they're both in the game of, trying to keep getting better and better over time, just in a different part of the curve where they're at. Any comments or questions before we jump into Chapter 5, because that's where we're at for the rest of the class? So now you know a little bit of the story behind Delta Sigma, and I suspect it's going to show up more and more in RF too, but another game that I haven't even talked about here is the fact that now what you can do is you run converters in parallel, so you can have one converter doing every fourth sample and then another one doing, filling in between, so you might distribute it over 4 A to Ds running at a quarter of the rate, and then you bring the results together, and then you have them matched because they're all on the same board, on the same die or something like that. So there's a lot of other things. It's a different game, though, for the RF side than it is for the audio side. The audio side just wants to get more bits of precision because of the needs of the demands of performance and things. But it seems like there should be a limit there because our human hearing is only so good. And when I was getting my MRI yesterday, my next door neighbor, who's an EE, retired from, he's a power systems engineer, we were talking about stuff, and he said, let me ask you a question. What about digital audio? People say that analog audio recordings are better than digital, and what do you think about it? I said, well, yes and no. I think some people were used to analog recordings and playback from a vinyl record, and they dismiss digital because it has other issues, but there's a lot of flexibility with digital and a lot of stability that comes from the digital. And so we talked about that while I was waiting to get called back for my scan. And then he said, yeah, as we get older, our hearing doesn't get any better, and maybe it doesn't really matter that much. And I said, I think you're probably right. And of course, Bluetooth and new advanced features of Bluetooth LE we talked about a couple weeks ago. That's pretty impressive that the Bluetooth like I'm wearing right now is the classic. The newer one has a better audio codec that can do better gain flatness audio bandwidth. This one cuts off at 12 kilohertz, and honestly speaking, when you're a young person, 12 kilohertz I don't think is good enough. You want more because that crispness to the sound is what comes from that very, very high end. Now, granted, that eventually goes away with age and abuse, probably both together, but still it'd be nice to have a little bit better. I can still notice the difference myself. If I listen to music on my lossless compression stuff on my iPhone that I took from CDs versus stuff that I play through the Bluetooth in the car, it's very, very noticeable. Does anybody else, can you notice that difference? This is not good enough by me, but it's $50 cheap, so but I think that'll get better. So that's maybe, and then the convenience of the Bluetooth and the other device and all the control stuff. It's sort of a package deal. I don't think it's just one thing. I don't listen to just one type of music either. If it's symphonic music, maybe more demanding. I don't really know. Okay, so moving on, chapter 5. This is a very nice chapter covering sort of bringing many things together. It can bring everything together that we studied so far, and it reviews certain things, and then it looks at some new things to go down the path on. So we're going to start with frequency response and look at some realities and some characterizations. Then we're going to look a little bit at system functions and stability. Geometric frequency response interpretation and using pole zero plots is pretty handy. That's in 5.3. And then a really new topic, I mean, everything up to this point is kind of things that you've seen probably from signals and systems classes up to this point, but this is in more detail. But then this is all the new stuff in here, and then that as well. The homework problems for set number 5 carry all the way through to the end of the chapter, kind of necessity, because historically I've always been pressing more for time at this point. So homework set number 5, I'm not going to be able to go through all of this before I leave in 40 minutes, so we'll finish up more of it next week. But you do have the hints out there already, and There's a few problems at the end that pertain to some of these other things, like the all pass and minimum phase and the relationship between them. I don't think I'm going to get into that, but I'll see what I can do. And if you're wondering what lies ahead, there's topologies, which is the actual topology of the digital filters and digital processing algorithms. That's Chapter 6. And then Chapter 7 is the FFT and application stuff. So those are the two things beyond Chapter 5. Chapter 6 has in it finite precision arithmetic too. And Chapter 6 is all, or Chapter 7 is all FFT and DFT related stuff. There's just a lot to all of this. So this is just a review. We had in the beginning, we had in the time domain, the first part of Chapter 2, convolution sum. Then we were able to get to the frequency domain with the Fourier transform. And then we were in Chapter 3 able to go to the Z domain. So those are all taken for granted. Which of these do you like best? I think your answer should be, it depends, right? I think a maybe is maybe not the right answer, but it depends is a good answer to say, what are you wanting me to do? What do you want me to give you an answer on? How does the system work? It works in the time domain, but you know, maybe we're doing filtering in the frequency domain. That can be done. We're still bringing a signal in as an X event and taking it out as a Y event, perhaps. So some limitations in understanding frequency response of LTI systems. We have h of e to the j omega. We have the magnitude in the phase. We have bad things that can happen. We can have distortion in the amplitude response, and then we can have phase distortion, which also is related to group delay. I don't know why the pen works so well now, and then sometimes it gets all stuttery. Something going on with caching, I guess, on my PC. But those are two things. Now, amplitude distortion and phase distortion are both going to be talked about here, but when you're talking about a filter like ideal low-pass filter here, there is amplitude distortion with respect to this entire band. It's very much amplitude distortion to pass everything here and block everything there. The idea of the distortion, though, is in the band of interest, what is going on? Is that flat or does it have ripples in it? And then what's the phase doing in that band of interest? So it's conditioned upon that. Everything has amplitude distortion and phase distortion, but not in the band of interest. I mean, it's well outside where we care, so it's with respect to that. But these are the standard frequency selective filters. If these could be plopped in and they were realizable, we'd use them all the time, but we can't do that. But they are references for the 4 different types. And there's a really cool homework problem in this set, which is my favorite problem, actually. You're going to look at some different block diagrams and try to explain what type of filter it's building, and it's using multi-rate and some other transformations inside of that. So don't remember the exact problem number, but let's just keep going. So a theorem that comes along early on, I'm not sure it's in the book, but I have it here in the notes, called the Paley-Wiener theorem, and it kind of tries to settle something that's been confusing or not sure for a very long time, and it just compacts everything into this integral expression. It says that if the impulse response has finite energy and it's 0 for n less than 0, which makes it causal, then the frequency response has to obey this integral right here. You have to be able to take the absolute value of the log of the absolute value and have it be less than infinity. So I kind of have this in here just for drama, to say this is a dramatization of that equation seems so far out in left field, like what can I do with that? But to me, the important conclusion oops. Is that if magnitude of h of e to the j omega were to be 0 over a band of frequencies, like we can have a stop band, then that says we're going to be taking the log of something, the natural log of something that's 0, and that's going to be minus infinity, but the absolute value of that is infinity, so we're going to be integrating something that's going off to infinity. If we try to make the stop band eliminate everything perfectly, we can only do that with a non-causal filter. So what our goal is to come up with realizable filters that can approximate the ideal filters and be causal. So this is the picture of a realizable low-pass filter, and these are some of the characteristics of it. We are allowed to have ripple in the pass band. We can drive that down to very tiny amounts, so it's essentially flat, no amplitude distortion, and then we have to settle for some rate of roll-off in the transition band. How rapidly do we want to come down through that? But then when we get into the stop band, we can't just wipe out all of these frequencies, because that violates the Paley-Wiener theorem, but we can choose to put ripples at certain selected points where we're tacking it down to 0, or we can have an asymptotic thing that's decaying towards 0 only when you get out to this point here. Those are some of the options. So generally the equal ripple can get us pretty good behavior with the least number of, with lesser complexity, but this just kind of gives you a picture about how that goes. This is also the picture of how you design an equal ripple, so-called equal ripple filter, and that's the Parks-McClellan, and I have that in my package. It's like a DSP-COM, the filters package can do that, this type of filter in low pass, high pass, band pass, and band stop, and it's been around for a very long time. It's a classical kind of design approach. Related to realizability and distortion is group delay. So group delay is, let me see where I'm at. Yeah, I'm going to be able to I have a very cool example here. This kind of will blow your mind out, the way what this example says. Only for certain people that would appreciate it. You know, the average person on the street would say, they would just be like, what are you talking about? But this, to me, is very cool, the way this works. And they added it to the most recent edition of the book. It was kind of interesting. I added it on my own when I taught out of the previous edition, the second edition, and then they put it in the third edition, and it kind of makes me wonder, why did they put in kind of the exact same example that I created on my own, but it doesn't really matter to me. It's in there now. But group delay refers to the idea that an ideal distortionless system or ideal delay system will just delay the signal by ND samples. Look at the frequency response of that, and we see a unity gain, and then what that delay does is it creates a slope. The phase is running downhill like that, a negative slope as omega goes up in frequency. That's an acceptable type of delay, where we have just a pure linear delay, and it's just, a linear phase shift, and that's due to a fixed amount of delay. If a system in its pass band can do that, we're very, very happy. I was looking at some audio systems from Shure. I just watched a video while I was eating breakfast because it came in my inbox, and it was for audio, for soundstage. And the one parameter that jumped off the page at me, which is a parameter of interest to me, is how many milliseconds of delay do you get with some wireless audio systems that are used for soundstage. You can get down to around 2 milliseconds. Is that good enough? And the guy in the video said maybe a drummer trying to get timed with his drum kit and everything, he needs better than 2 milliseconds. He can't perform. He said, well, then we have analog systems that can go faster than that. But in the DSP with the RF and the added latency that just comes about with all that processing, 2 milliseconds is what this Shure audio system can do. And I've always been told that at 10 milliseconds, if you're doing a two-way conversation, if it starts to get to the point where the delay between the back and forth, high, by, jumping in and out, both sides, if it gets to be greater than 10 milliseconds, it becomes annoying for humans. Our brains start to get very frustrated with that much latency. And satellite communications, you just can't make it faster because it has to travel out and back, depending upon the orbit it's in. But so that ND there just kind of comes to mind. The Pi Audio Helper system has an enormous amount of round-trip delay in it. You won't really notice it because you're just passing it through. But if I was sending it from a microphone and listening to it, which was done in the lab, it's very noticeable, and it's very difficult to deal with that. If you're talking into the microphone, hearing your voice, and then you hear it come back into the headset from the delay of the PC audio system, it's too much. It's not good at all. And that's been solved for soundstage with certain drivers that they can add to various types of laptops and things that might be used in soundstage. So if we build an ideal low-pass filter, what we're saying is we can tolerate just that linear delay. And that's used as a representation. But here's my take on what happens in a narrowband signal. So that, because that's this thing, linearity of phase can be grasped in the frequency domain with the idea of group delay. So group delay says we have a signal at a carrier frequency or a sinusoidal frequency of omega naught. We might have some amplitude fluctuations on it that change with time, S of n, but we have the band of frequencies either side of the omega naught going to zero. We have so-called bandwidth of that signal. So the idea of the group delay is that we can do a Taylor series expansion on the phase response just in that neighborhood of omega naught, and we can come down to this model of saying we could have delay on the envelope, which is the S part, and then we get a linear phase term on the frequency omega naught from that same time delay. And that's okay, that's acceptable. So that idea of group delay has to do with saying that in that band of frequencies, the so-called group delay will be a constant. And the way we get a handle on that is the definition. The definition says we take minus the derivative of the phase with respect to frequency. So this gives us a function of time. It's a time parameter in samples. In the DSP case, in microwave and RF, it'd be microseconds and things of that sort. Maybe the high-speed boards that you do, it might be picoseconds, I don't know. It gets sound really tiny, but transmission lines in general are constant group delay because they're just delay elements, but if they start deviating from that, then you have problems from a distortion standpoint. But deviation from constant, and that's what group delay turns into. So the way I like to think of it, and we're going to look at this example next, is group delay. It's saying the word group means a group of frequencies. When I send a signal through a system, the group of frequencies, which is around this omega naught, all sees about the same amount of delay. If the next group of frequencies over from that receives a different amount of delay, then we have, if we have to send a wideband signal through that, then we have different amounts of delays in different parts of the band of interest, and then that's unacceptable. Classical example of that I first got exposed to when I worked with fiber optics. When I was first in industry, I got to work with fiber optics and laser diodes and things like that. Why did I do that? my boss said that's what you're going to get to do next. I worked on an internal research and development, and I was using multi-mode fiber, and multi-mode fiber, when you couple into that for direct modulation, the amplitude is what's fluctuating, like the S of n, and we're sending high-speed data down there, which is going to turn the laser light on and off, or maybe make it brighter and dimmer. And the multi-mode fiber has got the characteristic similar to a transmission line, but it's not. It supports multiple modes, and there's a dispersive behavior to that, where some frequencies travel faster and some travel slower, and that causes a distortion in the pulses, and that means your information can't get received without having pulse distortion, which lowers the bit rate that you can send through the fiber. Why am I rambling on all that? Is because that's been the backbone of our networks across the country for decades now. The single mode fiber has very little group delay distortion, so you can send very high data rate signals across that, many gigabits per second, and you can send multiple wavelengths through that too, so one fiber can carry lots of information. They've been digging up our neighborhoods all over the city for MetroNet, and the other one that's further south, but that's a delay sensitive problem as well. The group delay distortion of wanting to have a wider bandwidth signal and not having problems with pulse distortion, because the pulse takes a wide bandwidth, and if one part of the information in one band arrives faster or slower, then it forms a pulse that's distorted. Interesting, right? I mean, this is a topic, I know Dr. Song talks about this in her classes, I'm pretty sure, but it really hits the road hard in common DSP, because we actually see the waveforms and the information and want to maintain the integrity, because we're trying to not have impairments, not have insertion losses with the delay distortion causing reduced or impeded performance. So an example I created here was to put in two narrowband pulse signals. They just occupy narrowband, send them through a low-pass filter, but the low-pass filter is going to have a bandwidth that's pretty flat. It's an equal ripple low-pass filter. So the information in this band of frequencies and this band of frequencies can go through this filter and not be really distorted from an amplitude standpoint. But what I'm going to do is use an all-pass filter on one of these, and the all-pass filter is going to purposefully take the delay distortion and make it be a very large number of samples of group delay. It's not perfectly flat, so that is an issue, but I'm saying this is flat enough because I just sort of rigged it up by trial and error, just playing around in Python in the notebook. So that pulse that has a band centered on the 0.125 is got a lot more delay than the band on the 0.25. So here's the time domain signal. The lower center frequency pulse looks like this. It's on a carrier, and it's just a pulse that turns on and off. And then here, one that's higher comes in later into my systems in terms of samples. When it goes through the low-pass filter, though, this has a lot more group delay than the higher frequency pulse. And this is the amazing thing. It's like a race to get through my system. The one that goes in first comes out last because of a realizable filter that's just hanging it up. It's holding it from getting through faster because of the group delay, whereas the higher frequency one comes out. This is what I said about amazing. For your average person, they'd say, I don't care. It doesn't mean anything to me. But to me, I find it's interesting, like with the exception of group delay, you would say a signal that enters the system first must come out first. Not necessarily so, and this is an extreme example, but kind of cool. Does it grab you, or does it just seem kind of so-so?
I don't think I understand it enough for it to grab me, but
Okay.
Very interesting.
It's real though. It's not, I didn't make this up. It's not artificial. You can build it and this thing could happen. So I guess what I'm saying is it could be if you had cavity filters or some other things going on that have group delay because they've been equalized to have a constant group delay, they still could have, as a result of that equalization, more group delay to make them have flatness. It could happen in a SATCOM system or something like this could happen. It's possible. I really don't know the example if this is realistic enough, but what it's just doing is saying intuition can be overcome by physical facts that your intuitive mind can't comprehend initially, but then the more you know, you're ready for that. So I don't see my watch. 15 more minutes. Next topic, though. So we've introduced group delay, and we'll just be using that as a measure. So we have amplitude distortion is from the magnitude response. Phase distortion is either, if it's not perfectly linear, then it has phase distortion. But linear phase, the derivative of that is a constant, right? And that's what group delay is. So they're related to each other. So a constant group delay corresponds to a linear phase response. And both of those are acceptable from a distortion standpoint. But the group delay tends to be more of a measure that people look to. You can measure that on a network analyzer in the lab. You can do it on a design for a filter. We'll be looking at filters later in this chapter. That'll be in the homework as well, that are linear phase filters. In particular, the FIR filters are perfectly linear phase, so their group delay is perfectly constant. And their favorite in designs, in digital comms and other applications, they require more increased complexity, but you're guaranteed stability and you're guaranteed constant group delay or linear phase from them. Next topic here, though, is just jumping over to say, what about linear constant coefficient difference equations? We studied them from the very beginning in Chapter 2. We studied them with respect to being causal, linear, and time invariant, that the coefficients are fixed. And we had pole and zero representations of them by factoring the numerator and denominator polynomials. We deal with the region of convergence always being the exterior of a circle of radius, being the maximum pole radius. This is kind of review of things that we've seen before about stability and causality. Just a review of that. This is a new item, though. This is not a big deal for me, but it's just a known fact. When you took second semester of signals and systems, Dr. Trimboli always teaches it. He's a control systems person, so he probably went through the Routh criteria. Remember the Routh? And you use it in controls all the time, right? So for DSP, this is the equivalent to that, is what it is. It's just another name, Schur, Kuhn, or Kohn. I'm not sure on the pronunciation, but the idea of the Routh array is you have a polynomial in the S domain, and you can prove whether or not you've got any poles that go to the right half side of the S plane. And here we're looking at a polynomial in the Z domain, and we're just interested if it's going to be a causal system and stable, we have to have all the roots inside the unit circle. So this can test for that. And it's just an algorithm, and it comes up with the answer. Now, it's interesting in its own behalf, but it's not something worthy of homework problems by me. What I'm interested in doing is just using the roots function, like the z-plane function that I have, of just taking the a and the b polynomial coefficients, putting in there, and just see what about the denominator. Where do the roots go? Are they inside the unit circle? So I'll just rely on the polynomial rooting function to tell me if the roots are all inside the unit circle. If you're rigorous, though, you'd say that algorithm could fail, and I wouldn't know, because it would be unable to numerically find the roots. Then I could go back to this test and actually run it and see if it's true or not. I put it in my notes in the beginning because I thought maybe it would mean something, but then there's so much other stuff that it didn't survive. Next interesting topic, though, is, and this is likely to show up on the midterm too, so something with an inverse system. If we have a system that introduces distortion, amplitude distortion, delay distortion, can we equalize it? And so what the idea would be, you would want this equalizer or inverse system. If it exists, then we can take and flatten the gain or make the group delay constant. And you're saying, well, why let the signal go through H of Z to begin with? If you're going to go ahead and equalize it, why did it go through H of Z? Well, the H of Z might be a channel. It might be a transmitter on Giant Mountain, and it might be foothills and multipath interference has got me. Did any of you watch TV on rabbit ears or an antenna in your house, or do you use cable?
Antenna.
Okay. Do you ever see any issues with?
I mean, usually rain and wind would basically distort it, and then you have to like basically
Move it?
move it to get.
You must live in line of sight of Giant Mountain then.
Oh, no, that was while I was in Nepal.
Okay. I live, right over here on the other side of the bluff. Well, there's many bluffs around here because this is Austin Bluffs, right, by name. But I have multipath. When I first bought my house, I put an antenna in the roof. In the attic. I didn't want to have it blow off. And I still can't get a line of sight, but I could try to manipulate it so that I could minimize the multipath, and it just wasn't possible. My wife likes to watch a lot of TV. I didn't really care that much. She let me fiddle with it after I spent some money at Radio Shack, and she said, we're getting cable. And it's never been the same. Both better quality, more money. It's really expensive these days, and that we use Xfinity, and we have our data service through them. Put that together with what you pay AT&T or some other provider. It's amazing. And all of us are probably victims of this or benefactors of it. We pay a lot of money for our infrastructure, for our personal use. It's just the way we operate. But in cellular and other things, this has to be dealt with. It has to be dealt with if you want to be able to have your call up and not be so frustrated that it doesn't work. So the cellular providers have put devices in the handsets to try to mitigate and create adaptive solutions, namely an inverse if possible. So this just says if it can exist. So one of the big conditions on creating the inverse, you would say the zeros in H of Z, you generally don't worry about the zeros causing instability, but now if you're going to build an inverse system, the zeros are the poles in your inverse system, and if they're going to be outside the unit circle, then you can't build an inverse system that's causal. So that's probably the biggest thing, and I do have an interesting problem because I was looking ahead for exam 2 that I've used in the past, and I'm probably going to give it to you. Why? Because I want you to explore it. You get to simulate it in Python, and you can get a really nice answer, and it works. It works. It works impressively well. You're going to have to come up with a causal inverse, though, and that is possible. And that's where minimum phase and some properties that we're going to look at come into play. So don't fear. It'll work really well, but I want you to actually do it because I think doing something means a lot more in terms of memory and stuff. So here's a system that H of Z, you'd look at this one and say, okay, I want to remove that distortion, so I'm going to let this be my inverse. just looking at it and from what you know right now, is that good? Is that realizable? The H of Z has got a pole inside the unit circle, so that's fair, that's causal. And the inverse system has a pole inside the unit circle too. It happens to be the zero from the system, and that's also fair. Or another way of looking at it, the way the book looks at it, the regions of convergence overlap so that the cascade is realizable. And you can come up with your inverse system, which has this as its impulse response, and send a signal that's an impulse that's gone through H of Z through this second impulse response, and it will remove all the distortion. What you'll do on the exam problem will be different, but it'll be making a realizable inverse. So it will start off not being realizable because the pole will be outside the unit circle. But then and I'll go through this. I think I have an example of that in here too, but it's not right here in the notes. Okay, moving onward, we use partial fraction expansions to get the impulse response for rational. Remember, we have residue Z that could help with that, so that's review. And then we can move into just looking at frequency response without going through the complexity of the impulse response. So we have a ratio of polynomials, and this is just factoring a high-order polynomial into individual roots in the numerator and denominator. And what is being driven at right here is how to individual poles and zeros in a system modify the gain, modify the phase, and ultimately modify the group delay too. So this would be, say, a particular low-pass filter that has a lot of ripple in the stop band, and it has a perfectly linear unwrapped phase. This is just a way of getting at the phase by unwrapping it. The idea of the wrapped phase you can lose the ability to see that the phase here, capital arg, means it's wrapped up to run between minus and plus pi, just like on a microwave network analyzer in the lab. It would wrap it up, but if you unwrap it, then you can see more clearly whether or not the phase is really, all negative, running downhill. And here, I took this example and unwrapped the phase, so you can see that it's just segments here that are continuing all in the same slope. So that means that if you differentiate this to get the group delay, or take minus the derivative of it, with the exception of these points where there's jumps, but those are where the nulls occur, so there's no signal that gets through the filter there. This has a constant group delay. That'll be looked at a little bit more later. Here's what the wrap phase looks like. I'm pretty much out of time. I have that other app that I'll probably bring up next week. We'll look at geometry. There may or may not be a geometry-related problem on the exam, too. I'm not really sure right now. It's kind of interesting. Did Dr. Tromboli have you do geometry? You guys that take him for 3205, do you do geometry, pole and zero geometries in there? That's the class he teaches right now.
Oh, Dr. Triboli?
Yeah. Did you ever do in the S plane though? Did you have poles and zeros for geometry? Yep. Okay, so that's this section in the Z plane here.
That was last year, Doctor.
I know, but I'm just saying that it exists, and you get to think about it again. Like if I put a pole or a zero in, things happen near the pole or the zero. So I'm going to go back over here. So be communicating more, not less, for the rest of the semester.